sono quello di prima. Dunque, questa volta, questo talk un po' più lungo, vorrei parlarvi di WebAssembly. E per cominciare vorrei chiedervi, quanti di voi conoscono già WebAssembly? Ah, pensavo di più. Quindi bene, perché almeno serve qualcosa. Insomma, perché questa è solo un'introduzione, volevo un po' raccontarvi la storia e le potenzialità di questa nuova tecnologia. Oh, sorry. This talk is in English. Apologize, I forgot. My English is terrible. I've lived 12 years abroad, and so if there is anything you will take away from this talk is that you can live abroad and work without speaking English. But yes, so this slide is to thank the sponsors, and I also would like to thank Marco Arena and the community. They are organizing this, this conference so well. So we are talking about web development, and which is unusual in C++ conference. A little history, as you know, the first real web browser was born in 1993, and initially the browser was not doing much. It was just markup with the ability to have hyperlinks and to navigate to text, and at most you could have some images. But in 1995, Netscape introduced JavaScript as a language to add some interactivity and the ability to modify and interact with DOM elements in your page. And the legend says that JavaScript was designed and implemented, the first version of the language that then was named JavaScript, by Ake in 10 days. So they didn't really take a long time and initially it was not really designed to do much, right? Just to add some interactivity to the web pages. But then at the same time, we had always the need to have something a little more complicated, something more sophisticated in our web pages. So there are many use cases. We like to run games, we like to play video, to have developer tools, I don't know. There are many use cases that require something that was not available in JavaScript, initially at least. And also, we have a lot of legacy code that we would like to reuse. And so the consequence of this was that other technologies were developed to interact with web pages as plugins, generally. Only when we run code in web application, we have strong requirements of safety, especially safety, really, security, and also portability, and that were not really satisfied by these technologies. For example, well, for a while, ActiveX controls were very popular with Internet Explorer, but they were not very safe. The safety was based on a trust model, on the certificate to sign the binaries. And managed plugins like Java Applets or Silverlight or Flash. Flash was very popular, but they had the security issues. Flash is still a source of security attacks, performance issues, and also portability, because if some platform does not support this technology, then the technology is going to die. And there was an interesting experiment called Native Client made by Google for Chrome. Native Client gave the ability to compile C++ code into x86 binaries, which were, however, validated before being executed. So the compiler was initially GCC, then also LLVM, was modified to produce some code that could be verified, validated, so that it could not do anything strange, or it could not access memory that it didn't own, or things like that. And so this worked very well from the point of view of security, but was not portable because it didn't gain a lot of traction outside the Chrome. Meanwhile, there has been a huge evolution in web browsers. So these are just 3 animated GIFs I could find that shows 3 kinds of websites. YouTube, Outlook on the web, and a map website. And you can see that nowadays websites are, web applications are real applications. They consist of tens of thousands, hundreds of thousands of JavaScript code. And writing web application is becoming more and more complicated, but it's also, we have a huge amount of libraries that we can reuse in the JavaScript world. So the ecosystem has grown considerably. We have frameworks like React and so on. But the result is that JavaScript, being the only language which is really available in the web, has become a universal language for user interfaces. And not only user interfaces, everything that has to run in a web application has to be written in JavaScript. Not exactly in JavaScript, maybe, because there are also other languages like TypeScript which add some static typing. And in any case, the JavaScript that actually runs in a web browser is not exactly the JavaScript code that is written by the developer. At the very least, this code is minified, and often all these libraries and frameworks are packed together with tools like Webpack and so on. So we are saying that JavaScript is also a target language. It's a language which it's used to compile or transpile or modify code so that it can run in web browsers. And the web browser, and this is very important, is becoming like a universal operating system. So it's abstracting functionalities from the real OS, like networking or the access to the file system, video rendering, and so on. And it's providing a universal API, which is available in any platform. So JavaScript as target language suggested the idea, Brendan Eich, that JavaScript could be really used as an assembly language. This quote is from several years ago, and it says, JavaScript is the x86 of the web. So since JavaScript is the only language that runs in our web browser, we could maybe think of writing code in different languages and reuse legacy code, or reuse the knowledge we have and work with Java or C# and so on, and produce JavaScript as a result. So there have been many examples of this during the years. GWT is a system by Google to write Java code that is then transformed into JavaScript. A similar thing is Script Sharp from C#. And TypeScript, I mentioned before. Elm is a functional language, which is also compiled into JavaScript. So we see that JavaScript, it can be used as a target language. But is it a good target language for compiling? Well, it's actually not too bad, because we have an idea that JavaScript is very slow, which comes from its past, because initially it was very slow. But nowadays, script engines are very, very sophisticated. What they do is, in a very few words, when they have a source file as input, first they parse their code and produce an abstract syntax tree. Then there are many levels of optimization that can be applied to this code. The first stage is just to interpret the code and to run it directly, as initially the script engine were doing. But meanwhile, the script engine can also keep profiling data up to date for each function, each block of code, which is executed. And when the script engine detects that some code path is particularly hot, so it's executed very often, what it can do is to trigger the generation of native code. So that piece of JavaScript code is translated into assembly code on the fly, possibly in a separate thread. And that the resulting code is very fast. There are benchmarks, depends on the kind of problems and so on, but the result is that JavaScript code can run almost as fast as native code. Only JavaScript is dynamically typed, so the script engine has a problem. What happens if the code generated for a function when it was called with a set of arguments with some sequence of types, like, for example, a string, a number, and another string. The same function is then called with other types. Then the generated code is invalid. So the script engine has to backtrack or bail out, as we say, and to go back to use the interpreter for that function. Now, why I'm saying this? Because practically the gist of this is that, yes, JavaScript code can run very fast, but it depends on how the code is written. So it's up to the developer also to not use patterns that lead to slow code. And from this came the idea of SM.js. I don't know if you heard of SM.js. SM.js is a subset of JavaScript which is optimized to be used as a target for compilation from languages like C++. This was an idea, was invented by Mozilla, somebody in Mozilla, around 2010. So why? Because they were working on, these were the same people working on the script engine itself. So they knew what make the JavaScript code slow or fast. And also they had this goal of trying to compile from higher level languages. Well, and what was the result is that if you define formally a subset of JavaScript and you remove some features that could lead to slowness, like garbage collection, then which is not used when you're compiling from C++ anyway, then the result is very easy to be run quickly in the script engine. So the script engine can generate ideal code for the compilation from C++. Or this is an example. For example, this is actually from some code, some program we'll see later. You have in C++ a class with a very simple function. And this is what, when we compile to SM.js, is the result without optimization. With optimization is like assembly. You don't understand anything because it's to optimize. But without optimization, we can see that it's really like simple assembly. And this is valid JavaScript at the same time. The bit is weird because there are things like or 0 everywhere, for example, which are used by to tell the compiler, to tell the script engine that this is certainly a number. So it can optimize right away the code because it knows that it is a number. And yes, how do you write SM.js code? The same people who invented SM.js worked on this technology called Enscripten, which is a LLVM-based compiler. So what they did is to take LLVM. LLVM can be used for many languages, like Rust, C++, other languages. It generates intermediate code, and they implemented a backend which generates, instead of generating assembly code, it generates SM.js. So it generates JavaScript. It generates exactly this kind of code we see here. Besides doing this, Emscripten is doing much more. It's actually also providing a number of libraries. For example, what happens if your C++ code is using the C++ runtime or standard library? Well, you have to convert all this code into the equivalent code that runs in a web page. And Emscripten takes care of all this. In general, there are a set of defined libraries in Emscripten that translate existing libraries like SDL into code that use the features provided by HTML5. So for example, for audio input, SDL code is translated into calls to the web audio API, WebGL, and so on. And this is very powerful because an existing application that uses, for example, OpenGL can be immediately translated into a piece of JavaScript code that runs in a web page with calls to WebGL, for example, instead of OpenGL. Now, as example, this is well, there are also the link, but of course, I don't have the network here. But this was an example that was done a few years ago of an x86 emulator running a virtual machine of Linux or Windows in the browser, which is the first time I saw this. I didn't have any idea how it could work. I didn't know that SMJS existed. And I was very surprised, really, because I saw that it was not installing anything. It was not installing a plugin or an ActiveX or anything like that. And still was working very well. And it's actually very simple because there is they took an existing emulator written in C++ for x86, converted to SMJS, and then what was left to do was just some glue code to make the emulator interact with the web page. So for the input, they were taking characters from using JavaScript and the usual web API. For the graphics, they were using probably a canvas or something like that, and driving into a WebGL, probably the canvas. So it's very impressive. It's very impressive what you can do with SMJS. Now, SMJS is still JavaScript, which is strong because it's supported by your browsers. JavaScript, as we said, is fast, is safe, relatively safe, and so on, but is not ideal as a language. Still, even with the optimization of SMJS, still JavaScript is not really a great language. For example, these SMJS files are huge because you can imagine there are all these assembly instructions that are implemented as JavaScript code. And the script engine still has to parse. The first phase, which we saw before in the execution of script code, is the parsing. And this is very expensive, especially in mobile devices. The parsing was really a problem with real big SMJS applications. And also, I mean, we are still talking of JavaScript, which what we want to do is not really JavaScript. So there was also the problem that while SMJS was being developed and new features were being added, they had to be added to the JavaScript language. So there was this duality in JavaScript from being used for the normal scopes and also being used as a target language in this specialized dialect. And they didn't really want to add new features just for that. So they had the idea of working on a new runtime that was available on all browsers, like JavaScript. But this runtime should be designed really to be an ideal compilation target. Still, with the same logic as before, so still to be used with tools like Emscripten. So that's how WebAssembly, or Wasum, as as is known, was born. And today, WebAssembly is supported in all major browsers, as you can see, even in the mobile version, supported in Edge, Firefox, Chrome, Safari, and also in Node. And it's really becoming a thing, really. Actually, probably you don't know, maybe you're not very familiar with WebAssembly, but it's likely that some web pages that you are navigating, browsing, is already using WebAssembly for some. Or, for example, Firefox is using, I think, WebAssembly internally for the, in the debugging tools for some functionalities like parsing source maps, because they could do this faster in this way. So it's really a thing that, that is taking place, important place. Now, let's look at WebAssembly in more detail with a very small demo. Now, this time, okay, it should work. I've written a simple function in C, actually it's not, to calculate a factorial. And using mscripten, which is installed in this machine, I can compile this code to into a file .wasm, which is a module, WebAssembly module, and then we will be able to load this module into a web page and call the factorial function written in C there. So the compilation is very fast. In this case, of course, that's 6 lines of code. And, well, EMCC is the compiler from mscripten. This is the file that I'm compiling, factorial.c. There are a few arguments just to say that it should only generate a module, because by default, mscripten generates also script code to act as a glue and to load the Wasum module, because the loading is still a bit complicated. Then we can go into our web page. And here, so this is this will be the result. This is a very simple web page where we can type a number and calculate the factorial. The web page has some logic for the DOM elements, but then what is interesting is that there is a call to load Wasum, and this function, what it does is to load this module that I have compiled. So here, let's go into the right folder. Yes, here. So from factorial.c, we have just compiled factorial.wasm. Yes, 346. So it's true. And here, I'm loading this file that I compiled. The loader does some magic, but what is important is that in the module, there will be an exported function called factorial, which will be able to call in our web page. So when somebody clicks enter in the text control, this code runs, which calls factorial of the number which was inserted in the text box. So we can do this, but to do this, I need to launch a web server. Wait. Yes. So now I am serving the content from this folder at this address in localhost. And then if I navigate, well, it's the same page. And you see. So let's look actually how it works with the debugging tools. What we have here is, well, it needs a refresh, yes. What we have here is a textual representation of the module that was compiled. And so now, well, there's no time really to go into the detail, but you can see that this is like the assembly. Wait. Oh, yes. Yes, there was more. Yes, this is like the assembly for C++ code compiled into native code. So the module defines, we will see later in more detail, but in a module there are globals, there are import tables, export tables, there are a number of functions. Each function is made by instructions, and the WebAssembly is based on a stack machine where each instruction pops its arguments from the stack and then push the result to the stack. The WebAssembly instruction set is made also with some control flow instructions like if, else, or a loop, or which make, and also this structure, the WebAssembly instructions are typed. There are types, there are only a few basic types, like int32, int64, float, and double, which, however, allow the script engine to validate the code before running it. So each module can be validated before being executed to make sure that it does not do anything that it should not do. And in particular, the memory is a component in the module. So each module can define a memory which is like a heap and that can be shared across modules. But the memory is separated from the code, the space or the others where there is the code. So there is no way to have buffer overruns or like attacks of this kind. So yes. So yes, web embedding is the fact, well, yes, that the module needs to be embedded in a web application, and so WebAssembly defines a JavaScript API for this. And also, normally, currently, the execution engine for WebAssembly is the same execution engine that exists already for JavaScript. So they are reusing the same logic. In particular, they are able to reuse all the backend logic in the script engine for the generation of binary code, which is already working very well for JavaScript. And so this made it possible to have WebAssembly working very quickly. Oh, sorry. There is a thing that I should not have here. Yes. Which are the notes? Okay. Finally, so yes, as I was saying, in a module, there are functions that are based on a stack machine, and structured constructs like blocks and if loops, and so on. And memories are separated from the execution stack and from the code space. And so a WebAssembly is, for this reason, is very safe. It runs in the same sandbox, the browser, as JavaScript. So yes, JavaScript, there are attacks also on browsers like Spectre, but they are quite rare. It's certainly much safer than running code, running native code in your machine. What about the speed? As you can imagine, being written just for the purpose of being a compilation target and being integrated in script engine that are already generating very fast code, WebAssembly is very fast, but is not really incredibly faster than JavaScript. This is not really the strength of WebAssembly. So if there are benchmarks also, these benchmarks depends on the kind of application. You can see that the fact that there is no parsing made it faster than SMJS. And, but the truth is that already JavaScript code can run almost as fast as native code in many cases. And so this is even truer for WebAssembly. In general, also in my test, I always found that the slowdown is like 1.5. So if you can run, I don't know, a game 60 frames per second in native code, will run maybe 40 frames per second in WebAssembly, which is slower, yes, but not too bad in the end. And yeah, also it's also very compact, the representation, the manual representation, which is important because these modules need to be downloaded, and so in the presence of a slow network, it's better not to download very large files. What about debugging? So let's go back to our browser. As you see, what we have for debugging is only the assembly code, which is a bit like having to debug C++ code without PDBs and without source files. So so it's not great, really. Actually, in this moment, the debugging is a bit a weakness of this technology. However, what you can already do is to set breakpoints in this assembly code. For example, this is the factorial function that was defined, compiled from C++. So if we change the number and call it, we'll see that the browser is already able to break in this position and show you in the locals the values for the registers that are being modified by the code, which is better than nothing. But for real debugging, the best thing would be to compile and run natively, and so with a real debugger. And then, from my experience, if it works with LLVM, it will also work later with WebAssembly, after compiling with unscripted. So before showing a couple of demos, I would like, so what is the point, really? Why would you like, why somebody want to run WebAssembly code? Well, not to replace JavaScript, for sure, because web developers are not likely to change language at this point. There is a lot of frameworks, libraries, know-how with JavaScript. So I don't see this becoming a new way of writing web application, normal web applications. However, as we said before, there are a lot of different kind of software that can require running native code in a web application. For example, and also there can be legacy code we would like to reuse in a web interface. The first example are games. With WebAssembly, WebGL, for example, the Unity engine has been ported, so Unity games already run in the web browser, which with all the portability that comes from that. But even more interesting is the ability to have just some components written in WebAssembly. Maybe because it's very CPU intensive, or maybe because we have already the code for that. An example is AutoCAD. They had decades of code written that runs their software on desktops. And they wanted to port some of their products to the web. So what they did was just to use WebAssembly to compile their code from C++. And from what they say, it was quite simple to have a working web application. Which, just imagine the alternative would have been to start writing JavaScript and try to convert all their legacy code from C++ or other languages into JavaScript. So yes, very I think many websites, there are websites that are already using WebAssembly for example, Bitcoin mining when we don't know. So yes, there are things like that. But the real interesting thing is that this allows us to get free of JavaScript. So we don't have to use JavaScript really for everything. We can use it for something, which are probably to drive the DOM, to control the user interface, but not for everything in a web application. And yes, so even though, as we'll see later, there are also already projects to use WebAssembly even for the user interface. An example. So this is a video game. This is an emulator for a very old video game called Galaga that I wrote a few years ago. And initially it was written in C++ to work with DirectX. Then I ported it to C# to work with Silverlight because I wanted to have it on the web. And finally, when I realized that there was unscripted, I compiled it to WebAssembly and made it work in the web. So this is interesting because it's an example where you have a component, which is the engine for this game, which is an emulator. It emulates the 80 processors and runs the original ROMs like MAME. And but this is like a black box. All the code in C++ is quite independent on the platform. Then when you have this code, you can give it input. You can ask it to run for n milliseconds, and then it will produce video frames and audio samples. And then you can have a host code that will render the video somehow and play the audio. But 95% of the code is platform independent and can be reused very easily. And the same way, with WebAssembly, we can have this Wasum module for the Galaga machine, and then take the video frames, audio samples, and use the Canvas Web Audio API to render. So just to show that it's true, so this is the project. No. Okay, so this is the project with, it's open source, it's in GitHub, with all the logic for the game, the emulator, and so on. And this is a very small web page that is doing the hosting. There is some code for the input and the rendering to Canvas. Well, we don't want to go into the details, but if we, so let's stop the web server here. I just compiled the game with unscripted before, so we have a file Wasum here in web application. Yes, this file Wasum, relatively small, and the host page. And then we can do node start server. Sorry, Galaga. Let me remove. Okay. This is booting. It will take a few seconds to boot, and then the game should start. There is also the audio, if you want, and you can. But well, it's now silent. So this is just an example of what you can do with WebAssembly. Another experiment, and however, this is an example, as I said, where you have like a simple page application entirely written with WebAssembly. So the web page is just a host, really. It's not a real web application. Another experiment instead was to try to use the normal DOM elements offered by HTML5, like in the API for the Canvas, to write a video game in C++. So I wrote a clone of Pac-Man. Same thing. Let's start. Yeah, Pac-Man. This is much simpler than the other game. But this is interesting because is implemented in C++, but using the HTML API. So I'm drawing into a canvas, calling line 2, and so on. Yes. So, for example, there is a class which is a wrapper for the canvas, which offers a API in C++ to draw into the canvas, and then the logic of the game is all in C++. So this shows that it's possible already to use WebAssembly in place of JavaScript for a web page. But nobody is going to do that, really. This was just an experiment. Final thing, yes. Last two things I would like to say are, well, that WebAssembly is working, it's already provided in all browsers, but there are many missing features because the people in Google, Apple, Mozilla, and Microsoft working on this, they focus on having a minimum viable implementation very quickly. So in a couple of years, from nothing, they got to this stage, which is quite good. But there are missing features, like there is no support for multi-threading, for example. There is no support for host bindings, which would make a better interoperability with the DOM elements to make writing code like Pac-Man easier. And most importantly, there is no support for garbage collection, which the consequence of this is that it's very simple to compile from languages like Rust or C++, but not from languages like Java or C# yet, which also could be a very useful feature. However, I don't know if you're familiar with .NET and Mono. Mono is this open source version of .NET. Mono has been, what you can do already is to compile the whole virtual machine for Java or .NET into WebAssembly. So Mono has already been compiled to WebAssembly, and using this, the SP.NET team in Microsoft is working on an experiment which is called Blazor, which is a way to have a kind of like SP.NET but working client-side with WebAssembly. So a way to have markup code interleaved with C# code in a web application. And this is working. You can find more documentation at that address. I'm not sure it's going to be adopted by a lot of web developers, but it's very, very interesting. It shows another way the strength of this new technology. And these are finally a few resources if you're interested about WebScript and WebAssembly. There is also a very nice paper written by I think then the slides will also be available probably so, with all the details. Questions? Yes? Thank you.
Okay. We saw two video games, two examples of graphics. So in the first one, if suppose it uses OpenGL and so WebGL in the compiled version. I haven't understood. Do I have to compile also an OpenGL library?
No, it's already provided in Emscripten. Emscripten comes already with support for a number of libraries for graphics, and for the standard library and so on. So for that, you already have everything working.
And for the second video game, we have seen interaction with the DOM model, which is the library that provides DOM model interface.
Yeah, it's still Emscripten. It's a class called val in Emscripten, which is a wrapper around a DOM object or a JavaScript element. So if I open the canvas class, maybe. Yes, you see, I have this Emscripten val data member, which is a wrapper on the canvas element in the page.
Okay, thanks.
Anyone else? Yeah.
How does the game loop work? Is it the game loop? How does it work? Is it actually getting ticks from the browser, or is the game loop?
For the game loop, I'm using, yes, in the browser. Wait, just a second. Yeah. There is, the loop is here. Start, repeat often.
But not too much.
Not too much. Yes, and it's using, yeah, I didn't remember, but it's using the request animation frame, which allows really the browser to decide when it's ready to ask for another frame.
Is it the same for Galaga as well? Is it the same for the other example?
Yes, this is actually what was running.
Yeah, okay.
Was running. Yeah.
Okay. So for external calls like to system or to some external, let's say cout was implemented something differently. I was going to like print to some terminal or some serial stream. How does it pan out with WebAssembly?
Can you repeat? Sorry, if you want to do what?
So, for example, you have abstracted, you said the standard library. So
yeah, this is done by.
So if I was going to, like, if there was a cout in my own program, it was probably going to print to the Java console, right?
Yes.
But what if I make a different system call? It's going to fail, right?
Well, no, yes, of course. Of course, it depends on what you are calling. If you are calling, for example, the GDI in Windows, no, there is no automatic translation. Somebody would have to write a library that transforms this set of calls into calls to, for example, Canvas. It's possible, but they have done just for the more important libraries.
Yeah, that's it.
Anyone else?
You listed a few features which are still missing, like multi-threading, exception support. So, but you said we can reuse C++. But what? How C++ features map to, let's say, known standards? It's not C++ 98. It has templates.
Oh no, you can compile. You can compile. It's LLVM in the end. So you can compile the latest features. I'm using the flag, for example, to enable here STD. Yes, STD C++17, for example, here, because my code base was already using Lambda, things like that, quite recent features of the language. Yes, if you are using features that are not supported, yes, you have problems compiling and linking, yes. The question was, what if the program is using multi-threading? Yes, of course, if there are things that make the compilation fail. You have to have a program that is not doing anything weird, otherwise it won't work. Good, thank you very much. Thanks.